Okay, let's get started. Hello, everyone. So my name is Haoyi, and this talk is going to be about how an optimizing compiler works. So there are a number of optimizers in the Scala ecosystem. You have the Scala JS optimizer, you have Scala JVM optimizer, you have the JavaScript JIT compiler, you have the JVM JIT compiler, you have the Scala LLVM optimizer. And the question is, if you want to write your own optimizer, how would you do that? Let's say any one of you wanted to say, I want my own Scala optimizer. How do you write your own Scala optimizer to do useful optimizations? So for most of people, the optimizer is a black box. So code goes in one end, and faster code comes out the other. The goal of this talk is to open up the black box, so all of you can have the intuition for how an optimizer works. You will not have a total understanding because that takes a lot of effort, but at least you'll have a sense of these are the kinds of techniques, algorithms, and data structures that go into an optimizer that are enough to make it do useful optimizations into your programs. So about myself, I'm a software engineer at Databricks. So Databricks does a lot of interesting work. You all saw Reynolds' keynote this morning. There's a lot of cool stuff, a lot of cool technology, and a lot of cool customer problems that we're solving. So we're hiring in SF Amsterdam and in China. So if you guys are looking for a job, you can come talk to us after the presentation. I also maintain a large amount of open source Scala tools. So who here uses one of these tools? More than I thought. OK. So glad you like them. But this talk is not going to be about either Databricks or my open source projects. Rather, we're going to go into optimizing compilation in 3 steps. First, we're going to hand optimize some source code in order to see what kind of optimizations you can do. Second, we'll talk about how the tool can model a program in order to achieve those optimizations. And lastly, we'll see how we can make an automated tool actually perform the same optimizations we did by hand, but automatically and in not too difficult a manner. So first, let's talk about hand optimizing some source code. So this is a small snippet of Java source code. I'll be using Java throughout this talk because it's a common language, everyone knows about it. It compiles relatively straightforwardly to its bytecode, and Scala normally converts relatively straightforwardly into Java. So all of you should be able to roughly read this and know what's going on. So we have a main function. It takes an argument, performs some computation, logging, returns a return value. For now, just ignore the fact that this function doesn't do anything actually useful, because the optimizer is meant to speed up your code and not question your business plan. So we have this piece of code. How do we optimize this? So first, we notice, well, this logger up here is not actually a logger. It's a print logger. And we know that because of the right-hand side of the assignment. Because we know it's a print logger, this logger.log function call can only go to one concrete implementation, which does system out of print line. So we inline that. Next, we can see that the multiplied variable, although it's assigned and updated throughout this loop, it's assigned here and updated here, it always remains 0 because it starts off as 0, and we're only updating it by multiplying it. So we can constant fold it and say, well, everywhere multiply is used, just put 0, and don't even bother with this multiplied variable. So we simplify it like that. The last few optimizations have left a bunch of code unused or dead. So this logger is not used, this Ackermann call is not used, this whole bunch of classes are not used. We can remove them. This if condition, 0 less than 100, always going to be true. We just remove the check and just directly perform the print line. And two of these Ackermann calls to the Ackermann function, have constant inputs. The first one, Ackermann 2 and 2, we know will always return 7. That's just the definition of Ackermann, and you can evaluate it yourself using this definition if you want, or look up the table on Wikipedia. And the second one, Ackermann 0 and n, we can look at 0, put 0 in here, and see Ackermann 0n always returns n plus 1 over here. So we can just put n plus 1 here and simplify the code further. Lastly, we can look at the last call to Ackermann, n and count, which we cannot partially evaluate because both inputs are unknown. But we can see that this function is pure. It does not have any side effects, does not do any logging, and it is only used within the body of the if conditional block. So because it's only used in if condition, we can late schedule it into the body of the if condition, null, so it never gets computed unless actually it's necessary. So this is what we end up with after doing all our optimizations. So count plus equals 1, multiply is gone, the if statement's gone, 2 calls to Ackermann have been either completely evaluated or partially evaluated, and the last call has been late scheduled into the if block. So this is the simplified code. And you can do this automatically because many of these optimizations I just showed you are extremely mechanical. You look at this is always 0, remove it. You look at this is only used later, move it later. This Ackermann call always has the same inputs, just evaluate it and put the result. So why can't we write a program to do that? So over here is a small demo I have with, here is the same code that we saw earlier. So it's an IntelliJ. I had to wrap in the class because Java wants you to do that. And over here, I have the compiled version of the same code. So this is decompiled using IntelliJ. So all the local variable names are gone. But it has more or less the same logic. You see var3 less than 100, var4.log, Ackermann22, Ackermann var3, var0. So this is a compiled version. The Java compiler doesn't really do any heavy optimizations up front. So all of the code here is almost as if we wrote it directly. So over here, I have a little optimize program. See optimize, and it's 11 megabytes of program. And I can run optimize on the source folder, give it the destination folder, and what method I wanted to optimize. Here's demo main, takes an int, returns an integer. So you run it, it turns away a bit, and now it spits out an optimized demo class file, which I can look at more. There, how do I make this bigger? F1. That's not it. Just use your finger was the correct answer. So here we have the optimized version converted using this optimized tool. And we can see it has done almost all of the same optimizations. The first call to Ackermann has been fully validated to 7. The second call to Ackermann has been partially validated to n+1. The variable names are gone, so it's called var0, but it's the same as the n we saw earlier as argument. The if statement here was removed. The log call has been inline because it knows exactly what the target, what the destination method is. And the last call to Ackermann has been late scheduled into the if conditional. So this is not quite exactly as you wrote it before. One, it's decompiled code, so it looks a lot uglier. Two, some things it's not quite clever enough to figure out yet. For example, this demo.println is still hanging around, being useless. But overall, it managed to do almost all the optimizations that we had done by hand earlier. So how? How does this 11 megabytes of optimize go and optimize our Java code to perform all these useful optimizations and spit out a program that you can then run and have the same output? Where are my slides? Why are my slides in the IntelliJ? Present. Okay, so in order to answer that question, first I'm going to go into how we model the program as a program inside the optimizer before I talk about how I use that model in order to make inferences and thus optimizations. So there are many ways of modeling a program. Perhaps the one that most people will be familiar with is as source code. So here's the Ackermann function we saw earlier as source code. So source code should be familiar with most of you. That's what you write, that's what you read, that's what you code review. But source code has some unfortunate properties. The biggest one is that it contains all sorts of miscellaneous information, which isn't really relevant to the execution of your program. So all of these three are the same program. And if you want to, you can write Java like Python. It just looks like that. But if you want to write, for example, something that uses a regex in order to analyze the source code and figure out what needs to change or what the source code does, it tends to be very error-prone. You can do it, but tools that use regexes on source code tend to require human oversight. For example, Facebook's code mod tool, which you would run code mod, see the refactorings it did, and then review it yourself to make sure it did something sensible. So that's okay for a refactoring tool, maybe not okay for an automatic optimizer. The next thing that we look at is abstract syntax trees. So abstract syntax trees basically take the thing that you parse out of the source code as a hierarchical tree structure and give it to you to work with. So here's abstract syntax tree of the Ackermann function we saw earlier. Here's it laid out as a diagram, as a tree. And you can see it more or less matches the hierarchical structure of your source code. So these are much more convenient to work with in source code, and many compilers use abstract syntax trees, especially in the front end, since that's what the really front end gives you. The parser will give you abstract syntax tree before you can do anything else to convert it to either separate representations or compile it to output. So the problem with abstract syntax trees is that they are pretty fragile in that you can have many different abstract syntax trees that refer to exactly the same program. And it's not even very difficult to do this. So here we have Ackermann A, Ackermann B, both variants on the Ackermann function. And they both refer to the same program as the original, but all three have different abstract syntax trees, which may seem obvious. But we can see here, we have this assign P, Q, all the idents have been replaced by P and Q. And here we have assign R and S, all identifiers have been replaced by R and S. Even though when your CPU is running, when your Intel i9 CPU is churning through your executable, it doesn't care what you call your identifiers in your local variables, or whether you're moving them back and forth. So this makes abstract syntax trees slightly harder to work with, because effectively what you have here is you have a tree. This tree has these assign nodes, these P and Q identifier nodes. For any node, if you want to know what that node does, you look at its contents. So if else, you need to look at equals equals return if else. Equals equals, you need to look at Q and 0. But for Q, you cannot just look at the contents of Q to know anything about Q, because Q itself is meaningless. It's simply a reference to this assign Q node up here. Effectively, what we have is a directed graph that happens to be embedded within our tree structure using these references of assignments and identifiers. This is an idea we'll come back to later. Next representation we look at is bytecode. This is the thing your Java compiler spits out when you compile it into binary. So on the right, we have the Ackermann function, same as earlier. On the left, you have the bytecode as a linear set of instructions. Bytecode works by executing top to bottom, and each instruction either moves something onto the stack, executes on the things on the stack. For example, maybe it adds 2 numbers on the stack, leaving 1 number, or maybe it returns the last number on the stack. Or it takes something on the stack and puts it back into a local variable array, which is over here. This function has no local variables, so the only local variables are the 2 input parameters, which kind of makes sense. So here you can see the stack getting bigger and smaller as it puts things on and computes things or pops stuff off. So the big problem with working with bytecode is that working with bytecode is pretty difficult to modify. So here, let's imagine we wanted to replace the Ackermann function at the end, the Ackermann call at the end, with a second Ackermann2 function call. And let's say it doesn't take the first parameter. We only want the second parameter. Why are we going to do this? Let's ignore for now. Let's just say we want to modify this function in a relatively straightforward way. So in order to do that to bytecode, you not only have to replace the instruction, which is down here, with Ackermann2, you also need to trace up the stack to see where the variable that is the first parameter came from, remove that instruction, look at where that variable's inputs came from, and remove those corresponding instructions. So even a small change tends to require changes, even a small change to your logical program tends to require changes all over your bytecode program. And that makes working with bytecode very difficult. Even a tiny change, reshuffle everything. Another tiny change, reshuffle everything. And that's both expensive and easy to get wrong as a programmer. So earlier we talked about the graph structure of ASTs. Let us now talk about data flow graphs. So data flow graphs are basically ASTs, but with all the assigned identifier pairs reified as fully fledged edges within the syntax tree. So here we see we have Ackermann, Ackermann A, Ackermann B, the three variants we had earlier that we know all do the same thing. And they all compile to the same AST, which is here represented with an n going directly to plus, to equals, equals, and to minus in this case. So the AST doesn't care how you're moving variables in and out of local variables or moving them on the expression stack. The data flow graph only cares where the value comes from and where the value goes. So in a data flow graph, the inputs to instruction are simply the incoming edges to the instruction. So if you want to do a modification, like replace Ackermann with Ackermann2 in this data flow graph, you replace the node for Ackermann, Ackermann2, you look at the edge that was the first input, remove it, and simply remove the upstream edges and the corresponding nodes from the data flow graph. So working with data flow graphs, basically every node in the graph, which is the instruction your program has execute, has direct edges from its inputs and direct edges to the places where its output is being used. So the fact that you have direct edges to basically everything the node cares about makes it very easy to work with the node, both to analyze it or to modify it if you want to change it during optimization. This description is greatly simplified, so there's a lot more detail around control flow, around managing of state, around exceptions and early returns, which I won't go into for now, but we can talk about later. So we've talked about hand optimizing some code. We've seen optimizations you can do, late scheduling, inlining, constant folding. We've seen that a program can do that automatically on a piece of bytecode. And we've looked at different ways in which we can model our program as a data structure to work with. So the last section of this talk will go into doing the inferences and optimizations to actually perform those optimizations given the data structure that we are constructing. So the first one will be type inference and constant folding. So type inference involves inferring constraints about the values in your program. Let's say you have a variable x. What's x? Is it an integer string? Is it an array? Is it a char sequence which has multiple possibilities? Is it something else? What do you know about this variable x can tell us what you can do to change the program. For example, if you know the variable x is of a certain type, then you can convert any as instance ofs, or you can remove any as instance ofs that are redundant, or you can convert any is instance ofs to either true or false, and propagate those to remove if statements, to do more constant folding, and do other sorts of optimizations. In general, the more things that you can infer about the program, the more optimizations you can do. So as optimizing compiler, the goal is to optimize to infer as much as possible, and then optimize based on those facts. So talking about type inference, types are usually modeled as a lattice. So here's a simplified type lattice, any integer char sequence with either string or string builder, and an array of floats. So in a lattice, if you have two things of different types, for now we'll just say that we're going to take the common supertype of those two things as a type of the value. So if I have a variable x, which is either a string or string builder, it's a char sequence. If I have a variable x, which is either integer or a string, we'll just call it any for now. So you can do this with union types and other ways of modeling it, but for now, this simplifies it for this discussion. Modeling singleton types in a lattice, which are basically constants, is also straightforward. An integer can be 0, 1, 2, or any other integer. A string can be any constant known value of the string. And you can basically treat these as any other types in your program. So if I have something that's either 0 or 1, you can assume it as integer. If something is either hello or world, you treat it as string. Hello or string builder, you treat it as char sequence, and so on. So singleton types really are just any other types with more specific information about the value being described. So let's go to inferring values on the data flow graph. So here is a data flow graph for the simplified version of this simplified version of the main method we looked at earlier. So I removed a bunch of stuff that we don't care about for now. We have this count equals 0 multiplied equals 0, while count's less than the input n. If multiplied less than 100, I log something. Increment count, multiplied. So there's a loop here, which makes the program a bit cyclic. And so you end up having a bit of a cycle in the data flow graph, which is why it looks a bit messy. But I'll walk you through this mess so you can understand what's going on. First, we start off at the top of the function in block 0. We look at this and see, well, it's assigning 0 to multiplied, 0 to count. So I can assign these two inferences 0 and 0. Next, the next block that executes is this count less than n thing. And this is to check whether to go into the while loop or just exit and go return directly. So that's highlighted here in the data flow graph. And I know that n is an arbitrary integer because it's an input parameter, don't know what it is. And I know count is 0 from earlier. So I know less than of between arbitrary integer and 0 is arbitrary Boolean. If goes to the if statement. I don't know what it's going to do in the if statement, but I need to analyze both cases. For now, let's ignore block 3 because it's just a return. Doesn't do anything interesting to our variables. Block 1b and block 1c, I will ignore as well since they also don't do anything to the variables, just to simplify it. And let's go to block 2, which is here in the program and here on the data flow graph. So count plus equals 1 corresponds to these edges in the data flow graph, where I take this count value, I add it together with 1. That gives me 0 plus 1 is 1. And I save it back into count. So what happens? I knew count is 0. Now I know count is 1. Count is either 0 or 1. Count is an integer. I do the same thing for multiplied. So multiplied times equals count. I take multiplied and count, feed them into times. 0 times the arbitrary integer is 0. I put that back into multiplied. And the common supertype of 0 and 0 is 0. So this tells us that after this part of the analysis, count is an integer, and multiplied is 0. So we just updated the inferred type of count. Previously, we thought it was 0. Now we think it's an integer. And so we need to propagate that change forward through the data flow graph in order to update anyone else who may be assuming that count is still 0. In this case, there are two downstream nodes. There's plus and there's greater than, or less than. So count as an integer, n as an integer. This becomes a Boolean, this less than block. Because it was already an arbitrary Boolean before, we can stop the propagation there, nothing changed. Count, which is integer plus 1. Integer plus 1 is still an integer, don't know what it is. It's an integer, and some integer. And I put that back into count, which is now an integer. Since we already saw count as an integer earlier, this does not need to, we can stop the propagation. And so we end up with this set of inferences for this program graph. Multiplied is 0. This times is always 0. So the times is the result of multiplied times count, which is always 0. Count is integer, and we already use integer. This less than is always a Boolean. This plus is always an integer. So now that we've inferred all this, we can then use this information to simplify the program quite straightforwardly. For example, we can take multiplied and just replace it with 0 everywhere it's used. And we can take all the code that computes multiplied, which we know is always going to be 0, and just remove that code since we know the output. So removing all that code from data flow graph, we end up with this simplified data flow graph, where block 0 just has one 0 that gets assigned to this count variable. It goes into this if statement, loops around a few times, incrementing 1 to count, and then returning something I didn't specify in this function. And this data flow graph can be serialized in a relatively straightforward fashion to this program. In reality, it's easier to serialize to bytecode rather than serialize to source code. But when you decompile the bytecode, you get this source program. So next thing I'll look at is interprocedural inference. So just now, everything was inside one function, and you had the loops, you had basic blocks, you were jumping around, but it was still within one function body. Now we will look at when there are multiple functions, what do we do? So here we have main and called. Main calls called, and then it returns the result of called after passing in 0 and n. How do we analyze this? Well, we start off with 0 as 0, n as an input integer, goes into called. Inside called, we have to analyze called before we can continue analyzing main, because what the inferred value of this called node is depends on what the contents of the called function tells us it is. So x is 0, y is an integer. You propagate that down. Times is 0, return is 0. Propagate that back out. Called is 0, return is 0. And we are done, and we see that this is our final inference, where everything is 0 because 0 times 0 multiplied by things tends to be 0. This is a simplified case, but the same can apply to other kinds of operations you do that constrain that affect the types that are being propagated. So now that we know this is 0, we can simply make main return 0 without all this rigmarole, and this is our optimized program and our optimized data flow graph. So next bit of fun is we are going to look at recursive interprocedural type inference and constant folding. So recursive functions are relatively common within Scala. Like functional programming loves recursive functions. And maybe for normal programming or normal compiler, you're okay with telling people to annotate the recursive function. But if you're a optimizing compiler, you want to say, this recursive function is pure, even though the person didn't annotate it. So how do you analyze something to figure out that this is pure, or this is constant, or this is something that's more specific than the person annotated, even though it's recursive, given how many recursive functions we tend to write in the functional programming style. So let's look at this. This is a pseudo-Java version of a factorial function. It takes an integer, and I just said it returns any. It's not real Java, but it's pseudo-Java. Let's just say we don't know what this returns yet. Or the code does not know what this returns yet. We can see that this clearly returns an integer. But how do we analyze that in a programmatic fashion? So on the right, you see a data flow graph. Here's block 0. It checks whether they're equals. If it's equal to 1, it returns 1. If it's not equal to 1, I subtract 1 from n, pass that into factorial, then multiply by n again, and then return that. And this is a recursive call to factorial and comes back to itself. So this is more or less one of the simplest recursive functions you come up with. But these techniques will generalize to other recursive functions, mutual recursion, more than one recursive call, etc. So we start off at block 1 again. In this case, the first block we see is n double equals 0. 1 is 1, n is integer, double equals of 1 integer is a Boolean. We don't know whether it's true or false yet. Because it's a Boolean, we have to consider both cases. So the true case is easy, we return 1. So 1 is 1, return is 1. The next case is more tricky. So in the false case, we need to pass in 1 and n into minus. So integer minus 1 is integer, don't know which integer. But when we pass into factorial, what do we do? Just a quiz, who knows what we do here? Okay, a few people know what we do. So this is not a new technique, but this is a technique that's more in the compiler backend field rather than the compiler front-end field. So what we do here is we say that there's a new type called bottom at the bottom of our type lattice. Bottom is below every other type, but other than that, it behaves just the same as any other type would behave. And you guys use nothing in Scala, which is basically the same as bottom, and you're familiar with it. So first, I come and annotate factorial as bottom. So I don't know what it is, it's bottom. And bottom proper cascades. So bottom times integer is bottom, and it returns bottom. So bottom, bottom, bottom. Next, what do we do? Well, now we know that this factorial function either returns 1 or bottom. And you can look up 1 and bottom in our type lattice and see the least upper bound is 1. So least upper bound is 1. I can take this 1 and place it back into this factorial call and say that the recursive call is now inferred to always return 1. 1 times the arbitrary integer is arbitrary integer. It now returns an integer. We can make one more round around this type lattice. What's the least upper bound of 1 and integer? Least upper bound is integer. Put that back into the factorial call. And feed that back into times. Integer times integer is integer. And because it was already integer for the last iteration, we can stop the propagation, and we're done. So this is our final inference of a recursive factorial function telling us that it returns an integer even though it was annotated to not return anything. So you may notice that if two of the cases we walked through so far, we have kind of an iterative propagation approach where we make one pass around the function or one pass around the recursive set of recursive functions, and then we have to keep propagating more passes until the inference stabilizes. So in general, anywhere that you have a cycle in your program, whether a cycle is a loop or whether a cycle is a recursion, you're going to need to do multiple passes of inference in order to get the most precise inference. On the other hand, if your program has no loops and no recursion, then it is possible to do one pass from topologically from the top of your program to bottom and get the most precise output. So the number of iterations we do is bounded. And the number of iterations we do is bounded because every time we go around this cycle of propagation, our types rise at least one level in the lattice. Because if the type did not rise, you would stop the propagation. So given a lattice of this height, the number of iterations is completely bounded by the height of the lattice. And if you want, we can control how we can trade off number of iterations against precision of inference by making our lattice more or less detailed. For example, we could easily have the lattice have a separate node for non-zero integers. Or the lattice could have a separate node for positive and negative integers. Or the lattice could have separate nodes for null or separate nodes for strings of particular length. And all of these allow us to more precisely model the program during inference and generate more precise inferences. But at a cost in that, because our lattice is taller, it may require more iterations around this data flow analysis in order to converge. So the last thing I'm going to talk about is liveness and reachability analysis. So liveness and reachability analysis are two pairs of related things which say this code never runs, or this code always runs, but it doesn't actually do anything. Its output's not used in the end of the program. And in either case, the code is safe to remove, and we can do so to make the program shorter, smaller, faster, without affecting its output. Let's look at this last variant of the main method, which I've mangled in a different way. Here we have this total variable, which gets aggregated and added to, but never ends up being used in the return value of the program. On the other hand, we have this count function, which does get used in the return count variable, which does get used in the return value of the program. But we have one update site, which is never going to get run. So total fails the liveness analysis and can be removed. This count plus equals 1 fails the reachability analysis and can be removed. So how do we do that optimization in a programmatic fashion rather than just squinting at it as humans? First, we can do the same constant folding we did earlier. So we know multiplied is always going to be 0. This is always going to be false. Next, we end up with this simplified tree or program and simplified data flow graph, where if 0 greater than 100, do this count plus equals 1. So looking at the data flow graph, we can see that we have 0, 100, greater than. This is always going to be false. And so the if statement can we can remove the false branch of the if statement and all of its downstream nodes in the data flow graph. So 1 plus this arrow are all in this are all in the true block and can be removed. So that leads us to this simplified data flow graph. So now we do the liveness analysis to say which code in this graph is not used in the return value of the program. And that ends up being a relatively straightforward analysis. You just start from the return value, do a breadth first search up the graph, and you see here all the black nodes are the ones that appear in my breadth first search. All the red nodes are the ones that do not appear in my breadth first search. So even though we have total adding to itself and depending on itself, and none of these nodes have 0 inputs or have 0 outputs, we know that total ends up not being used, and this greater than node ends up not being used. So we can remove these from the data flow graph, giving us this, which is a simplified data flow graph of the earlier function with all the rubbish removed. Total is gone, the if check is gone, multiplied is gone. Simple graph, starts from 0, loops around a few times, around this conditional if statement, increments count, and returns at the end when the if statement fails. So So to wrap up, we've seen some optimizations that we can perform manually. We did type inference, inlining, constant folding, dead code elimination, branch elimination, late scheduling. There are many more you can keep doing, and you can list them out. If you go into any compiler textbook, there's going to be a whole chapter full of different optimizations you can do one by one. After we did them all manually, we saw that you can write a program that will run over your class file and do all the optimizations automatically. So rather than spending your human brain power to do so, you just rely on a laptop to turn away and spit out a more optimized program. Next, we look at the modeling of a program, the different ways in which you can say this is a program data structure in memory, and the different trade-offs of how easy it is to work with them, analyze them, or modify them. For this demo, I used data flow graphs, both for the implementation of the program you saw earlier and for the slides here. But you can do the same work on ASTs or bytecode, just with more or less effort depending on which representation you choose. Lastly, we looked at how to do these inferences and optimizations automatically. We saw type inference, constant folding, how constant folding really is just type inference with singleton types. And we saw interprocedural inference, when you have one function calling the other and analyzing both one after the other. And we saw how to do recursive interprocedural inference, where if you have a recursive function, how you can analyze it taking advantage of this bottom sentinel node in your type lattice in order to do multiple iterations around the data flow propagation and end up with the correct answer. Lastly, we looked at the two other optimizations, which are not type inference and constant folding. We looked at liveness analysis, which is removing things which are not used in the final output. And we looked at reachability analysis, which is removing things that will never get run, even though if they do get run, it will affect the output. And we saw that how we could do this using relatively simple data structures. This is just a directed graph with maybe some cycles in them, and relatively simple algorithms, which is just traversals over the data flow graph, possibly making more than one cycle, and finally stabilizing and using the inferred values or inferred types of your program in order to make the optimizations. So I didn't come up with any of this stuff myself. All of this is well known in parts of industry. So if you're interested in learning more about optimizing compilers and you want to go and write your own Scala C optimizer, Java program optimizer, or even optimizers for other languages, most of these techniques will transfer relatively easily from Scala to Java to C# to C++, maybe even to JavaScript, or maybe not. And these two books, I think, are a good reference, where Engineering Compiler is a very thorough reference of the general architecture of a compiler with many sections, many chapters based on optimization techniques. And combining analyses, combining optimizations by Cliff Click, that's his PhD thesis from 1995, is a good introduction to this idea of data flow graph modeling and data flow graph analysis using this particular technique. So that's it for how an optimizing compiler works. I think I might have a bit of time for questions, so have at me. Reynold? Yeah. Oh, so the question is, I did not talk about how I go from class files to data flow programs. So let's go back to the class file representation. I can go into a bit of detail since I have some time. So going from ASTs to data flow programs is easier. You just take these identifier assigned edges and you make them into real edges, and that's your data flow graph. So going from class files to data flow programs is a bit trickier. But if you look at how class files look, you see as we move things on and off the stack, for example, here let's look at this section where we load the first argument, put the constant 1, subtract it to get another value, load another constant 1, invoke static to get another value, and then return it. So these abstract variables, they're called, being moved on and off the stack, basically form a set of edges between the node which constructs the abstract variable, for example, node 22 I sub constructs v4, and the node which consumes the abstract variable. In this case, I believe this one would be number 27, no, wrong, number 30, invoke static. So if you follow these nodes along the virtual stack, you basically end up with a graph of where the values come from and go to, and that is your data flow graph. So if you want to learn how to do that, you should go look at, it's called the ASM Java Bytecode engineering library. So they have a very good tutorial for data flow analysis, specifically converting data flow from bytecode to data flow graphs using their library. And that's what I used for the demo earlier. I didn't have to write it all myself. Any other questions?
Do you have benchmarks?
I do not have benchmarks. So unfortunately, this is not quite at that stage yet. So I've demoed it working. I have not demoed the efficacy on top of the JVM JIT or other JITs.
And is it going to be open source?
I don't think it's in good enough state to open source. It's a bit of a mess. Yeah. But I don't think you'll get much from reading the code. So if you want to know how it works, this is basically everything about how it works on these slides. Yeah. In front here?
And when you do the interprocedural analysis, do you consider the context?
Yes. So if you look over here, where am I? If you look over here where I'm propagating the 0 from the main function to the call function, basically that means I have to analyze called separately for every different parameter it gets. So obviously this doesn't scale. If I call with 1,000 different functions, I don't want 1,000 different duplicates. And you have to prune those with heuristics. Like the JVM says, if there are 3 different dispatches in the polymorphic call site, it just treats it as polymorphing, doesn't try to inline. Similarly, for this kind of thing, you have to prune it eventually, say there are too many different contexts to analyze it within. I'm just going to take the conservative view. But that's also another thing you can trade off. Like, if there's only one call site and one call function, it's very easy to propagate the context. 0 goes to 0, this gets optimized beautifully. If I have 2 call sites, it's also easy to propagate the context, especially if they both have constants. If I have a million different call sites with different contexts, then maybe you may decide you have to start collapsing them in order to make the analysis more tractable. But that's a thing you can trade off and turn a knob to go higher or lower precision or higher and lower performance.
Yeah, you mentioned fusing map and filter and things like that. It said in the talk description.
Yeah, so I don't have the demo here now, but fusing map and filter is basically inlining once you It's basically inlining to a concrete function. So if you have a map function and you copy the map function with only one lambda, you can then inline through that lambda and map function to effectively fuse it.
Sometimes if you want to build a map, but first you want to transform a list and you want to do something, you can save a lot of performance by creating a view.
Yeah, so it doesn't do that kind of fusing, but it does the inlining to primitives kind of fusing. Not sure if that's the correct terminology, might be the wrong terminology. But basically converts like chains of options flat maps into straight line code. It does not work on arrays yet. It does work on array seeks due to implementation problems. But in general, a lot of this stuff is not production ready yet. It's mostly a demonstration of the principles.
What does a side effect look like in the data flow graph?
That's a very interesting question. So this data flow graph analysis technique is basically copied from Cliff Click's thesis. And Cliff Click's thesis ended up in the JVM that you all are running as a hotspot optimizer. So if you go look at the hotspot documentation, it'll talk about that. In short, it looks a lot like a IO monad. So you basically have nodes which take in a world and pass out a changed world as a separate value. And so these nodes have more than one output value, and the ones which are pure will not need to take in or return the world, and the ones which are stateful will take in and return the world. And when you do the graph traversals that we showed earlier, all of it kind of flows beautifully. I mean, it doesn't need that much special casing. Any other questions? Up at the back.
I perceive the talk as a general introduction to optimization of compilers, but it would be interesting, like, what's your application in the end in the Scala ecosystems? Like, where you're planning to do this kind of optimization? Is it a compiler plugin, or like, what's your goal?
It's unclear. I have what I have now. It kind of works. What to do with it is not that obvious. In principle, it should be able to do much more aggressive optimizations than the Scala C optimizer can do, because Scala C optimizer doesn't assume a closed world. It still allows multiple separate compilation. If you consider how much does the Scala JS optimizer speed up Scala JS code, does anyone know? Andrea? No, the question is how much? I think it's something like 2 to 10x, depending on the code. So you can get very aggressive optimizations once you do a closed world analysis. So in principle, if you can get 2 to 10x speed up of Scala JVM code, or even 1.5 to 5x, that would be pretty cool. But that would be a lot more work than this demo. Any other questions? At the back there.
Hi.
Hi.
Thank you very much for the talk. Nice introduction to the subject of the optimization. Just to clarify. Oh. Yeah, sorry for the microphone. So it was a very nice presentation, introduction to the subject. Your optimizer, is it working on the bytecode level, bytecode to bytecode, or on the Scala source? Or?
This optimizer works on the bytecode. So it does the same technique I described earlier, where you walk the bytecode in order to build a data flow and control flow graph. It's arguable which one is better. I was using bytecode because that's more well-defined, and I'm more familiar with it.
Is it based on ASM by any chance?
Yes, it's based on org object web ASM, at least for the front-end parsing and graph construction. After that, ASM doesn't do anything.
Okay. One thing I was curious, one of the techniques one of the techniques sometimes is missing in Scala, particularly if you do a bit of more functional style or pipelining, is usually something called deforestation, the process by which you're not optimizing the code, you are like cutting away intermediate data structures.
Yes, I can talk about that. So deforestation basically requires heap analysis, which is a separate field of program optimization I did not touch on at all. So yeah, I have not implemented heap analysis, and therefore this does not do either deforestation, unboxing, escape analysis, none of that. And that would be its own project.
Oh, and one last thing, if I may.
Yeah?
Another thing I'm thinking is that if you have, you prefer the functional style of in Scala and you like to pass around a lot of higher order functions, now those end up being implemented as polymorphic calls, and you end up like having, if you have like a lot of calls to list.map, you may end up having like several references to an object that then can have many lambdas, right? The implementation of function one objects in Scala. How well does the optimizer achieves with that?
It would take more time to describe than I think we have, so I can come talk to you later after. Yeah. I think we are done as far as time goes, so thank you for listening.